Before watching this video, I would recommend that you re-watch videos 9 and 16 to remind yourself about some of the history behind neural nets. As we've seen in video 16, a single neuron cannot simulate an exclusive OR gate. Understanding why this is the key to helping us understand what simple ANDs can and cannot ultimately do. Consider the neuron on the screen which has two inputs. The activity of this neuron is expressed by the sum of its weighted inputs as shown by the formula on the screen. Now, supposing we plot the inputs on a graph as shown. We can rearrange the equation shown above to represent a straight line on this graph. What this line represents is the boundary between those values of I1 and I2 which produce a 0 output from a neuron and those values which produce a 1 output from it. This representation assumes that the squashing or activation function is a threshold. If it were a sigmoid or a different function, it would be a broader transition band as shown. Now, I explained in previous videos that a single McCulloch-Pitts type neuron could not simulate an exclusive OR gate, and we can now see why by looking at the diagram on the screen. I've represented all 4 inputs and the outputs on the graph. The inputs which should produce a 1 output are shown as a shaded circle, and those inputs which should produce a 0 are shown as empty circles. Now, I hope you can see that no matter where I place the dividing line produced by the neuron on the graph, I cannot separate the inputs producing a 1 from those which are producing a 0, and therefore this neuron cannot reproduce the truth table of the exclusive OR shown. In the language of ANDs, we say that the exclusive OR gate is not linearly separable. As an exercise for yourself, you can have a look at the other common gates and show that these can be simulated and are therefore linearly separable. Now that we understand linear separability, it's easy to see how a simple network can simulate an exclusive OR gate. Supposing we had the 2 simple neurons as shown on the screen. We can then AND these 2 together to give a required output. Remember that the AND function is reproducible because it is linearly separable. Of course, when Minsky and Papert pointed this out in 1968 in their book Perceptrons, there wasn't an obvious way of training a multilayer network, and hence its effect on the whole subject of ANDs. But now we have backpropagation and other algorithms which can train multilayer networks. As we'll see in the next few videos, this theory has much to tell us about the capabilities of networks and how big they need to be in order to solve particular problems.